Welcome to Don't Forget to Subscribe. Imagine a warm Friday evening in July 1981. The air in Kansas City is thick with humidity, but inside the brand new Hyatt Regency, the atmosphere is electric. It is Tea Dance Night, a nostalgic trip back to the 1940s that has drawn a crowd of over 1,600 people into the hotel's sprawling sun-drenched atrium. The sound of a big band orchestra fills the air, echoing off the glass and steel. Couples are swirling across the floor, while hundreds of others line the balconies and the three spectacular sky bridges that span the lobby, suspended in mid-air like ribbons of concrete. Then, at exactly 7:05 p.m., the music is punctuated by a sound that no one can quite identify, a sharp metallic crack, like a gunshot, followed instantly by a thunderous roar. In a heartbeat, the fourth-floor walkway groans, splits, and begins a sickening descent, shearing through its supports and slamming into the second-floor walkway directly beneath it. Both massive structures, weighing tens of thousands of pounds, plummet into the crowded dance floor below. Within seconds, a scene of elegance and celebration is transformed into a tomb of twisted steel, shattered glass, and pulverized concrete. But here is the most chilling part. This wasn't an act of God, a bomb, or a natural disaster. It was a catastrophe born from a single simple drawing, a sketch on a piece of paper that changed the fundamental physics of the building. Later in this video, we are going to reveal the specific design shortcut that turned these luxury walkways into a 64-ton guillotine, a revelation that still haunts the engineering world today. To understand how such a prestigious project could fail so spectacularly, we first have to look at the sheer scale of the object itself. The Hyatt Regency Kansas City was the crown jewel of the city's urban renewal project, a $50 million architectural statement, equivalent to roughly $170 million in today's currency. Completed in 1980, it was a 40-story tower of modern luxury, but its centerpiece was the atrium. This wasn't just a hotel lobby, it was a glass-enclosed cathedral of light, measuring 145 feet long and 117 feet wide. To give you a sense of the scale, you could comfortably fit an entire professional football field inside that lobby and still have room for the sidelines. The ceiling soared 50 feet high, nearly 5 stories into the air, offering a panoramic view of the sky through its massive skylights. Crisscrossing this void were the three legendary sky bridges. These were not mere aesthetic flourishes, they were engineering feats designed to connect the hotel tower to the ballroom and restaurant areas. The second and fourth floor walkways were stacked directly on top of each other, while the third floor bridge was offset to the side, creating a visually stunning, multi-layered environment. Each of these walkways was approximately 120 feet long and constructed using heavy steel box beams, reinforced concrete slabs, and glass railings. The sheer mass involved was staggering. A single walkway weighed approximately 64 tons. That is roughly the weight of an M1 Abrams main battle tank, or a herd of 10 full-grown African elephants suspended right over the heads of the guests. When you stood on the floor of the atrium and looked up, you weren't just seeing a bridge, you were seeing dozens of tons of dead weight hanging by slender steel rods that looked almost delicate against the massive backdrop of the building. It was a design intended to evoke a sense of weightlessness, a modern marvel that invited people to stand and watch the world go by from 40 feet in the air. On the night of the disaster, the live load, the weight of the people, added even more stress to the structure. While the bridges were designed to hold large crowds, the visual of hundreds of people leaning over the rails to watch the dancers below created a scene of perfect, albeit precarious harmony. Everything about the Hyatt Regency screamed safety and sophistication. This wasn't some fly-by-night construction project in a backwater town. It was designed by GCE International, one of the most respected structural engineering firms in the country. It had been constructed by the Eldridge Construction Company and thoroughly vetted by city building inspectors. It had received its certificates of occupancy. It had passed every legal hurdle required by the state of Missouri. The materials were certified, the permits were in order, and the public had no reason to believe that the ground beneath their feet or the ceiling above their heads was anything but rock solid. Yet beneath the polished marble and the shimmering glass, a fatal mechanical flaw was ticking like a time bomb, waiting for the exact moment when the laws of physics would override the stamps of the inspectors. The disaster at the Hyatt Regency didn't begin on that July evening. It began years earlier, in a series of phone calls and scribbled notes between two offices. To understand why those walkways fell, we have to look at the fast-track construction method used for the hotel. In the late 70s, time was money, and the Hyatt was being built at a breakneck pace. This meant that construction often began before the final blueprints were even finished. This environment created a breeding ground for a catastrophic lack of communication between the lead engineers at GCE International and the steel fabricators at Haven Steel Company. The original engineering design for the walkways was ambitious but theoretically sound. The plan called for a series of continuous 45-foot-long steel hanger rods. These rods were supposed to be anchored into the ceiling of the atrium, pass directly through the fourth-floor walkway beams, and continue all the way down to support the second-floor walkway. In this single-rod system, each walkway would hang independently on the same rod. Each walkway would only be responsible for supporting its own weight and the weight of the people standing on it. It was elegant, simple, and, crucially, never built. When Haven Steel received the blueprints, they realized they had a logistical nightmare on their hands. A 45-foot threaded rod is an incredibly difficult component to manufacture and transport. Imagine trying to move a steel needle the height of a 4-story building through a crowded construction site without bending it. Furthermore, threading a rod that long is nearly impossible with standard machinery. The entire length would have to be threaded to allow the nuts to be screwed all the way up to the 4th floor level. Haven Steel proposed what they thought was a simple, common-sense solution. Why not use 2 sets of shorter rods? In the revised plan, one set of rods would connect the 4th floor walkway to the ceiling. A second, entirely separate set of rods would then hang from the 4th floor beams to support the 2nd floor walkway. To the layman, it looked identical. To the steel fabricator, it was much easier to build. But to an engineer, this was a fundamental shift in the physics of the building. This change effectively doubled the load on the connection points at the 4th floor. Think of it like this. Imagine you're hanging from a pull-up bar with your hands. That is the original design. Now imagine a second person comes along and grabs onto your ankles. Suddenly, your hands and arms aren't just supporting your own weight, they're supporting the weight of the person below you as well. In the Hyatt Regency, the 4th floor box beams were the arms of the structure. In the original design, the nut on the rod only had to support the 4th floor's weight. In the new design, the nut on the 4th floor beam had to support the 4th floor and the 2nd floor simultaneously. When the change was proposed, it was communicated via a telephone call. The lead engineer later testified that he believed he was only approving a minor detail. No one, not a single person, actually sat down to perform a recalculation of the load capacity for the new double-rod configuration. If they had, they would have discovered something terrifying. Even without a single person standing on the walkways, the revised design was already stressed to its absolute limit. The structural integrity of the entire system was operating with a safety factor of almost 0. The beams themselves were another point of failure. They weren't solid blocks of steel, they were box beams made by welding 2 C-shaped steel channels together. The hanger rods passed through a hole drilled directly through the center of these welded beams, held in place by a nut and a washer. This created a massive concentration of stress at the exact point where the beam was weakest. The yield strength of the steel, the point at which the metal stops being elastic and starts to permanently deform, was being tested every second the building stood. There were warning signs. During construction, a large section of the atrium roof actually collapsed. An investigation was launched, and the engineers assured the owners that the building was safe. They even performed a cursory recheck of the entire structure. Yet, because the walkway change was considered a minor field adjustment, it was never re-evaluated. They checked the wind load on the exterior glass and the seismic load on the main tower, but they ignored the 64-ton guillotines hanging in the center of the room. As the dancers moved to the music on that July night, the vibrations of their feet created a rhythmic dynamic load. This wasn't a hurricane or an earthquake, it was just a few hundred people enjoying a party. But that small extra force was the final straw. The steel at the 4th floor box beams reached its ultimate yield strength. The metal didn't just bend, it punched through. The nut and washer literally ripped through the center of the beam. Once the first nut slipped, the load was instantly transferred to the remaining rods, which snapped like guitar strings in a horrific chain reaction. The point of no return had been reached and gravity took over. The clock on the wall read exactly 7:05 p.m. when the laws of gravity finally collected their dead. For the 1,600 people in the lobby, the first sign of the apocalypse wasn't a visual one, it was a sound. Witnesses described a series of sharp rhythmic pops, like a string of firecrackers or a hammer hitting an anvil, as the nuts on the fourth floor hanger rods began to tear through the steel of the box beams. In a fraction of a second, the fourth floor walkway shifted. There was no slow creak, no warning groan. The steel simply reached its limit and surrendered. The fourth floor bridge, carrying dozens of spectators, plummeted 30 feet through the air. It struck the second floor walkway with the force of a falling building, and together nearly 130 tons of concrete, steel and human lives smashed into the crowded dance floor below. The entire event, from the first structural failure to the final impact, took less than 7 seconds. To put that in perspective, it takes longer to tie a shoelace than it took for the Hyatt Regency's crown jewel to become a mass grave. The scene that followed was one of primal, unadulterated chaos. A thick, suffocating cloud of white concrete dust rose from the wreckage, coating everything and everyone in a ghostly powder. The cheerful big band music was replaced by a deafening, terrifying silence, followed quickly by the screams of the trapped and the dying. The hotel sprinkler system had been severed, and thousands of gallons of water began to flood the atrium, mixing with the dust to create a thick gray sludge that hampered rescue efforts and threatened to drown those pinned beneath the slabs. The lobby floor, once a place of celebration, was now a jagged landscape of twisted rebar and shattered glass. The human cost was staggering. 114 people were killed and 216 were injured. These weren't just statistics, they were families out for a Friday night dance. There was the story of a young woman who was pulled from the wreckage after hours, only to realize that the person she had been holding hands with was no longer there. Rescuers, including off-duty doctors who had been attending the party, had to make agonizing battlefield decisions. Dr. Joseph Weckerly, the team physician for the Kansas City Chiefs, arrived to find a triage site that looked like a war zone. He and other medical professionals had to perform on-site amputations with chainsaws and pocket knives just to free victims from the crushing weight of the concrete. Firefighters and volunteers worked through the night using jackhammers and massive cranes to lift the 32-ton sections of the walkway, often finding that the weight had been so immense that the victims beneath had been completely pulverized. As the last of the survivors were pulled out, the focus shifted from rescue to the hunt for the truth. The National Bureau of Standards, or NBS, dispatched a team of forensic engineers to the site within 24 hours. Lead investigator Edward Frank walked into the wreckage and immediately noticed something peculiar about the hanger rods. They weren't broken. The rods themselves were intact, hanging from the ceiling like skeletal fingers. The failure hadn't been in the steel of the rods, but in the connection points where the rods met the beams. The investigation was a masterclass in forensic engineering. The NBS team took the debris to a laboratory and reconstructed the punch-through failure. They discovered that the revised double-rod design was a death sentence. According to the Kansas City Building Code, the walkways were required to support a load of 302 kilonewtons. The original single-rod design would have met this, albeit narrowly. However, the modified design that was actually built could only support 181 kilonewtons, barely 60% of the legal requirement. On the night of the disaster, the dead weight of the walkways, combined with the dynamic load of the dancers, meant the structure was carrying 169 kilonewtons of force. It was operating with a safety margin of almost zero. It wasn't a question of if it would fail, but when. The fallout was swift and devastating for the engineering profession. The Missouri Board for Architects, Professional Engineers and Land Surveyors charged the lead engineers at GCE International, Jack Gillum and Daniel Duncan, with gross negligence and unprofessional conduct. While they weren't sent to prison, the punishment was a death blow to their careers. They were stripped of their professional engineering licenses in multiple states, and their firm was shuttered. The investigation revealed a terrifying truth. The engineers had signed off on the final drawings without ever actually looking at the revised connection detail. They had trusted the fabricator had trusted the process, and in the end, 114 people paid the price for a signature that was never earned. The legal battles lasted for years, resulting in over $140 million in settlements, but the scars on the city and the engineering world would never truly heal. The dust from the Hyatt Regency collapse did more than settle on the ruins of a hotel. It settled on the entire profession of structural engineering, forcing a total reckoning of how we build our world. Before July 17, 1981, the process of reviewing shop drawings, the detailed diagrams created by steel fabricators, was often treated as a bureaucratic formality. Engineers would stamp these drawings with "review only", a phrase intended to shield them from legal liability if something went wrong. The Hyatt disaster tore that shield to pieces. The Missouri Board of Architects and Professional Engineers made it clear: if you sign the blueprints, you own the consequences. This led to a fundamental shift in global engineering standards. Today, the engineer of record is legally responsible for every single connection, every bolt and every weld, even if they didn't draw it themselves. This is known as the Hyatt Rule, and it is written in the blood of those who died that night. The American Society of Civil Engineers, or ASCE, underwent a soul-searching transformation in the wake of the tragedy. They adopted a new policy that made the safety of the public the paramount responsibility of the engineer, superseding loyalty to the client or the employer. This sounds obvious today, but in 1981 the lines were blurred by the pressure of fast-track construction. The Hyatt Regency was built using this method, where design and construction happen simultaneously to save time. This is like trying to draw a map while you are already driving at 70 miles per hour. The pressure to stay on schedule and under the $50 million budget created a culture of assumptions. The fabricator assumed the engineer had checked the math. The engineer assumed the fabricator was following the original intent. This game of professional telephone ended in a 130-ton collapse. Sadly, the Hyatt Regency was not the first time engineering hubris led to a mass grave. Decades earlier, in 1907, the Quebec Bridge in Canada collapsed during construction, killing 75 workers. The cause? A world-renowned engineer, Theodore Cooper, had ignored warnings that the bridge's weight was exceeding his calculations. He was too proud to double-check his work, believing his reputation was more solid than the laws of physics. Just like at the Hyatt, the error was a simple one of load-bearing math. Because of the Quebec disaster, Canadian engineering graduates started the tradition of the iron ring, a ring worn on the pinky finger of the working hand, supposedly made from the scrap metal of the collapsed bridge. It serves as a constant, cold reminder against the skin that an engineer's mistake isn't just a typo, it is a potential tragedy. The Hyatt Regency serves as the American equivalent of that ring, a permanent scar on the history of construction. The hotel itself underwent a massive $5 million renovation and reopened just months after the disaster. The walkways were replaced by a single massive bridge supported by heavy columns rooted directly into the lobby floor. There are no more hanging rods, there is no more illusion of weightlessness. Today, the hotel is known as the Sheraton Kansas City Hotel at Crown Center, and for decades there was no sign that a disaster had ever occurred there. It wasn't until 2015, 34 years later, that a dedicated memorial was finally unveiled in a nearby park. It features 114 names engraved in stone, a silent testament to the lives cut short by a missing calculation. This disaster is a mirror of systemic decisions. It shows us what happens when good enough becomes the standard in a high-stakes environment. It proves that a catastrophe is rarely the result of one big mistake, but rather a Swiss cheese model of failure, where the holes in communication, the holes in oversight, and the holes in the physical design all line up at the exact same moment. The 114 people who died in Kansas City were not killed by a freak accident. They were killed by a series of small, mundane choices made in quiet offices months before the first dancer ever stepped onto the floor. Engineering is more than just math and steel. It is a moral contract between those who build and those who live within those buildings. When we walk across a bridge or enter a skyscraper, we are placing our lives in the hands of people we have never met. The Hyatt Regency collapse reminds us that this trust must be earned with every single signature. If we value speed over safety and profit over precision, the laws of physics will always be there to remind us of our error. What do you think? In our modern world of move fast and break things, are we still at risk of another Hyatt Regency scale disaster, or have we truly learned our lesson? Let me know your thoughts in the comments below. If you found this deep dive into the mechanics of catastrophe insightful, please hit the like button and subscribe to the channel for more stories of human ambition and its consequences. Your support helps us continue uncovering these forgotten chapters of history. See you in the next one.